All right, so we'll get started now. Hi guys, my name's Alex. I'm one of the course assistants for CSU24W. I just graduated from undergrad in the spring. I'm a co-term student in computational and mathematical engineering. Just a few things, like this is an overview of snap.py. Cut me off whenever you feel like you need to ask a question. There's not too many of you guys here in person, so like if you have any specific questions, feel free to raise your hand. I'll call on you. And then also, if I can stick around after for a little bit and answer any specific questions you might have, because I know we haven't had office hours yet. So just a few things before we start. One is, like, you don't need to worry about taking furious notes. The slides are going to be online and on Piazza. The second thing is that Snap is much more expressive and can do much more than what is described here. So I put a link to the Snap documentation, and what you can see is there's a whole bunch of, there's a little tutorial, a reference manual, and then you can search things, for example, like load edge lists, if you want to load the edge list of a function, and you can see that it's, right, that there's a function that does that. So before you go and reinvent the wheel, look at the Snap documentation, because there's a good chance there's a function that does what you want. Second thing is, Snap is not all powerful. For a lot of the stuff, like in the homework, in your project, like Snap is not powerful enough or expressive enough to do exactly what you need to solve your problem. And so sometimes you need extra data structures to be able to solve the problem. So like an example of that is, I know you guys definitely haven't looked at it yet because it came out like 12 hours ago, but on the last part of the question 4 on homework 1, you're going to need supplementary data structures to store what nodes in the graph are diseases and what nodes in the graph are genes. No worries, that doesn't make sense. And other times you need a data structure to store, for example, like a mapping from a node's ID number in Snap to like the real world name of it. So like a map from like a disease ID to what the disease is, for example. So what is Snap? Oh, there we go. So what is Snap? Snap is the Stanford Network Analysis Platform. And the big things, right, is the analysis and manipulation of large networks. And the big thing is, so it's developed by Stanford, it's developed by Yuri's lab, and one of the important things is that it scales to massive networks that have millions or billions of nodes and edges. And what that means for us, as the users of it, is that it actually runs on a C++ backend, and snap.py, which you guys, or Snappy, I don't know how you actually say it, is a Python binding on top of that. And that sort of explains why you can't just use the adjacent, like a lot of the networks that we're going to work with in this class are real world. And so you can't just use a NumPy matrix and just manipulate and work off of the adjacency matrix to solve every single question in the homeworks. And then sometimes sort of the awkward syntax that you have is a result of the fact that snap.py sits on top of the C++ libraries. And that's why you see some things like vectors, ints, strings sort of reinvented. So there are a bunch of resources. There's pre-built packages, there's documentation, and a mailing list if you have questions, but there is a small community of people outside of Stanford who use this, and it will be helpful to you guys to engage with it. There are also developer resources if you're looking to build legitimate software systems on top of Snap. There's also, this is more relevant, not for necessarily the homeworks, but actually for your final project, is that there's a bunch of network data sets that Yuri's group has collected at this link. If you go to it, what you'll see is that they have a bunch of different graphs from Facebook, Twitter, voting, a bunch of different stuff that could be good inspiration for your projects when that time comes. Installing it, since there's not too many of you here, I think the best way forward is for me to, if any of you guys have questions at the end, I can walk you through it. But there's some instructions right here that are linked to download and install Snap. And if you're on a Mac, just so we can kind of like just explain what this gibberish is with the command line, you download it. There's a .tar.gz file, which is basically a zip file. The first command unzips it. The second command moves you into the directory. And then you hit install, or you type the install command. and it should work. In addition to Snap, a few other libraries, and I'll send links out afterwards, a few other libraries that are useful for this class are NumPy, which is like the standard library for numerical computing in Python, and then also PyPlot, which is a library that allows you to make pretty graphs in Python, and that I think is easier to use and more expressive than some of the native Snap functions. And then if you have problems, there's a troubleshooting guide. Go look at it. It addresses a lot of the most common installation problems. If you want to use a virtual environment for Snap and for all your projects, there are also someone posted very graciously instructions on Piazza on how to do that. If you don't know what a virtual environment is, don't worry about it. So then in terms of actually using snap.py, you gotta, yeah, what's up?
Are we using Python 2.7?
Oh, yes, sorry. That's a good point. Is you have to have Python 2.7. You cannot use Python 3 for this class. So to my understanding, there is no Snap for Python 3. Yeah, before I start getting into it, any other questions? Cool. So yeah, so obviously, in order to use the Snap libraries, you need to import it. And then but beyond that, there's also a more robust tutorial on the website that has a lot of these examples. And basically what we're going to walk through today is, OK, what are the basic data types in Snap? How do vectors, hash tables, and pairs work in Snap? Hint, it's almost exactly the same as normal Python. The basic graph types, how you instantiate a graph and manipulate it by like adding and traversing nodes or edges, and then a few useful functions. But then again, just a reminder, like this is just kind of the tip of the iceberg of what Snap can do. It actually is much more powerful. And so before you go and implement something yourself, check and see if Snap has it already. So basically, just sort of as a rehash. And again, the redundancy is because it's Python binding to a C++ library. So you need to basically reinvent the int, float, and string types. So there's tint, tfloat, and tstring that you need to work in Snap. Then they correspond to int, float, and string. Then for vector types, you actually need to, in Python, you usually don't need to say what's in a list. But in a vector, in Snap, you need to oftentimes declare vectors that are then passed by reference into functions. I'll explain later what I'm talking about, or you'll see examples of it. And you need to explicitly say what types are in the vector. So that means that you can't just say, oh, I have some list, like you would in Python. You actually need to say, if you have a vector of ints, it's a t int v, and that's just the naming convention for vectors. It's like t value type v. And you can do a lot of the same things. You can append things, get the length, index into it, and iterate over all the elements. And so just a quick little code example, right? You can add a bunch of stuff. You create the vector, you add a bunch of stuff to it, you print the length of it. One quick call out there is that on the length, actually, that's different than the syntax of getting the length of a Python list. Just keep in mind. You can get and set elements. You can iterate over the elements. As you can see down there, index in. Just one thing to call out, even though it is a vector of ints, right? You don't actually need to convert the numbers. You don't actually have to convert 4 to a tint before you add it to the vector. You can just add the int 4. Any questions on the vectors? Cool. So then, sort of in that vein, there's the same thing for hash tables. So you know that a hash table or hash map is a set of key value pairs. And here we impose the additional constraint in Snap hash tables that keys have to be of the same type, values have to be of the same type, but obviously value and key do not have to be the same type. And there they have, again, a naming convention. It's t, key, value, h. And that's, so then a map from int to float would be t int float hash map. And then there's a few operations, right? You can add a new value or set one, get the size, and it looping through it for I in the map loops through the keys. So pretty straightforward there. And then here's just a quick code example for the hash table. So again, you create, in the first line, you create the hash table. And then you add a bunch of elements to it. You get the size. You can set element values, iterate over the keys. So it's pretty straightforward. And then there's it's the same thing. I don't want to bore you all, but there's the same thing going on for pairs. And so the pairs are like a Python tuple, except you now need, you need to specify the types of each element in the pair. So you have an int t, int string pair, t int float pair, t string int pair, and there you can get the first value and get the second value. So like that. You will not interact with these too much, but they're still important to understand. So I guess for these special pairs, vectors, hash maps, so the way that you would most often interact with them is there are a lot of snap-specific functions. For example, to calculate the degree distribution, you can use there is a snap function that does that, and it takes in a hash map or vector, I forget which one, but it takes in one of these data structures that's passed in by reference. And so then in that context, you would need to create one of these vectors and then pass it in to the snap function that computes degree distribution. So the most important thing, and what you will be working with on every single assignment, is where I'd pay attention, are the basic graph classes. So I don't know who came up with these names or why, but tungraph, okay, is the undirected graph type. So like we talked about in lecture, edges have no direction. There's an edge from A to B. There's an edge from B to A. It's all one and the same. tngraph is a directed graph. So the only difference is a U. And then there's this tnea net thing, which is really, it's a multigraph with attributes on nodes and edges. So what does that mean? It means it's probably more, I know it is definitely more expressive than either of the two other graph types. And a multigraph means where you can have multiple edges between nodes. You can give nodes properties in the graph rather than having to maybe store them in a separate data structure, stuff like that. And let's see, is there anything else I want to talk about on that side? No, we're good. So then just an example on graph creation. So right in the first line, importing snap again. And then, so these last two lines are just creating undirected graphs and multigraphs. But then, so I'll focus on the lines about G1, right? So the first thing that you're doing is you're creating the graph. That's just the syntax for creating a brand new graph. And then you're adding a bunch of nodes, and you're adding a bunch of edges. And there's a few important points about that. So the node, first, that nodes have to be added before you add edges. So if in this graph I tried to add an edge between 5 and 14, there is no node 14. So it would throw an exception because node 14 is not in the graph. And then similarly, node IDs have to be positive integers in Snap. What that means is I can't have a node with ID S. They can't be strings or any of that. And they don't have to be in increasing order. So right, like what you saw here, for example, is I have nodes 1, 5, and 12, but there's no nodes 0, 2, 3, 4. Like they don't have to be in linearly increasing order. And just this is important for the homework assignment because unfortunately you guys will have to do a little bit of data cleaning. On the disease gene network problem, for example, the disease IDs are they have a C at the beginning of them, and so you actually have to do some manipulation to make it work with Snap because it will not take C it will not take node IDs with strings in them. So it's just something to keep in mind. So then one of the things you're going to do dozens of times in this class is traverse a graph. And so the first one is, so there's 3 small code snippets here. The first one loops through all of the nodes and prints the node ID, the node degree, other stuff. The second one prints the edges, or prints all the edges in the graph, as well as the source and destination IDs. And then the last one what it does is it goes through all the nodes and then does sort of, I think the technical term for it is in order, but then for each node, it prints all of the neighbors of that node in the graph. And the important things here, if you're looking up, if you want to look up documentation, is for the node and edge iterators is on Snap, there's two specific classes. One for node it's like t_ungraph node I, so that's a lot of words, and then there's t_ungraph. Sorry, I'm definitely not writing large enough. t_ungraph edge I, and what these are these. They're technically called node iterators and edge iterators, but what they really are like references to the actual nodes in the graph data structure. And that's what allows you to access certain properties of the node. So you can, the most important ones are, you can get the ID, you can get all the neighbors, you can get the degree, stuff like that. And if you're looking for what you can do with a node iterator, it's these two functions in Snap. We'll do that. So then the second thing, or after traversing a graph and creating a graph that you're going to want to do, is you're going to be able to save and load a graph. So, did you have a question?
Yeah, I was wondering if you can expand what you mean by ID of a node.
Yeah, so if you remember here, when you're adding a node to the graph, it has to have a positive integer ID associated with it. And so that's what, for example, like 1 and 5 and 12 are. There are nodes with IDs 1, 5, and 12. Yeah.
Can the attributes be lists?
I will get back to you, but I do not think so. I will write that down. Yeah.
And when you traverse the graph, what order will it like go over it? Will it like go through like IDs from small to large, or like the order at the moment?
I'll look that up again. I'm not sure, but for most use cases, you won't need to have it in any specific order of node ID, if that makes any sense. Like like for the algorithms that we're going to be implementing, most of the time, the order that you traverse the out edges doesn't necessarily matter. Yeah.
Let's say I want to create 20 different nodes. Is there a way I can put that into a for loop?
Yeah, you could. Well, yeah. If there's a naming scheme that you have for your nodes, say.
For example, add node, and then I have I and I that through the numbers. Will it think I'm trying to label that node?
No. It'll pass the. It'll like. So if you could do like for I in range 20.
Okay.
Graph dot add node I, and it'll work. It'll make a graph with nodes 0 to 19 in it. Anything else? Cool. Yeah. So then,
Internally, like which representation does it use? Because the complexity will sort of depend on that. Right?
Representation for
Like
the graph.
lists or like adjacency list matrix.
I would guess not an adjacency matrix, but I'm not entirely sure, but I'll look it up. I would guess adjacency list, stored in some smart data structure. So yeah, so for graph saving and loading, the big things are if you want to save a graph, say you've created a graph, done some manipulations, you want to save it somewhere, you can do that. There's more documentation on the website. You can load it as well. That's going to be a pretty common one. And I will show you more detail on that on the next slide and what that means. And then there's also this .graph file format that I don't think is particularly necessary, but it exists. And you can use it to save it to binary files. That's helpful if you want to actually, like you can, instead of creating the new, basically the difference between the bottom half and the top half of this slide is that the top half, you have just like a .txt file that you can open. And then as you load it in, you actually have to create all the nodes and edges in the snap graph. It's like how it works. Whereas in the bottom half, you basically like convert your snap data structure to a binary file. And then that file gets loaded, so it's a little faster. Sorry, the top is, you will get most of your files in text files. Most of your data sets are in text files, as you'll see on the next slide.
For the homework, we got like pre-processed text files, but like I think for future classes, would we have to clean like and assess?
So most data sets that are designed for network analysis will have a structure somewhat like this one. So it will never be perfectly clean, but and we're not trying to make this class an exercise in data cleaning. So most of the time it will be in a very convenient file format. But what you might have to do is like play around with the header, header a little bit sometimes. And then, so yeah, just to continue on, like this is an example of a text file that you would get, but that has a graph. And the snap load edge list function assumes when you give it .txt file, it assumes that every single row in the text file encodes one edge, and it ignores the rows at the top of the file that have hashtags, $signs in front of them. And so yeah, that's just how it works. And then the documentation here is if you see snap load edge list, it takes the graph type, the name of the file, and then it takes the source column, the destination column, and the separator. I don't know why the separator's not there, but the source column would be 0. This is only relevant if you're looking at a directed graph. So the source column would be 0, and then the destination column is 1. If you were making this an undirected graph, then like switching the order wouldn't really matter. But it still needs to know what 2 columns in the file represent edge lists. So like for example, on the homework, you're going to get a file that's like this. Oh, this is going to break. It doesn't do well with text files. But the point is there's 8 columns in the file instead of, come on. If you open it up, you'll see that this text file, which is a bunch of disease and gene associations, has 5 columns. And what you really want are the first column, which has the gene ID, and the second column, which has the disease ID. And that's what's relevant to us. And then one thing I'd also want to call out, because this is also relevant to the homework, sometimes, like a lot of times, this snap function to load an edge list works great. I mean, it always works, but sometimes the use case that you have for it, or that you have for the graph, sometimes it's not expressive enough to do that. So what I mean by that is, consider the example from the homework again, where you have a graph that has both genes and diseases on it, but you need to track which nodes are genes and which nodes are diseases. If you just use the load edge list function, you are not actually going to know that, like which node numbers are genes and which node numbers are diseases. So you actually might need to sometimes manually loop through the text file yourself. Does that make sense?
The library in itself does not handle node types.
So yes, you can, for example, like in multigraphs, you can add node types or node attributes, but sometimes I think it's just easier to loop through, to use secondary data structures. It's probably not the best code style, but in terms of getting it done, like in terms of your code working quickly and you know it working, I think that like having supplementary data structures is fine. Yeah.
Can you think one more time why alone edges would not work for the gene side?
It would work. So you could put in that it's like the 0th column is the source and the 2nd column is the destination. It's just that alone won't give you the disease or gene attribute. Like it's dependent on the homework. Like the homework question makes it clear because you need to do operations that are specific to the genes and specific to the diseases. And you need to have, I'm not going to go like give away the answer, but you need to have some mechanism of telling like node ID 5 is a gene or node ID 5 is a disease. And that's not immediately intuitive, like that's not immediately clear, and you would have no way of knowing that if you just had a graph that you loaded from the edge list.
Our concatenation of characters and numbers, and how are those loaded as nodes?
Yeah, so that's what I was saying earlier. Is you actually can't in Snap the node IDs have to be integers. So you have to do a little bit of manipulation.
So then would load edge list now? Would it?
Yeah, so it would do. Yeah, it would
work?
return -1 or throw an exception. I forget which. Anything else?
So generally each node will have a feature set, right? Associated with it.
What do you mean by like the properties of the node?
Yeah.
Yeah. So in the undirected in the Snap undirected graph type and in the Snap directed graph type, they will just be node IDs with a set of neighbors. Well, like they'll be nodes, and then they'll have a bunch of edges out of them to other nodes, and that's it. And then you can add, and so all of these things are in the documentation. So if you go to like TNEAnet, you can see there's a bunch of all the way down. Yeah, so you can see that there's somewhere you can add integer, float, or string attributes to it. So yeah.
For that disease data set, is there like a better way to load a file?
Not that I know of. So yeah, part of that question is, right, you load a bipartite graph, and then question 4, you're gonna have to fold it over to create associations between diseases based on whether they have a gene in common. So we'll learn next week during lecture about ways that you can manipulate bipartite graphs to learn interesting things about the graph structure and the relationship between the physical objects in it. But to load a bipartite graph into the, you just got to use the normal operation. Oh yeah, sorry, homework 1. Yeah, sorry. This is sorry to clarify. The disease gene stuff is on homework 1, not homework 0. There's nothing to do with homework 0. Homework 1 went out last night at midnight, so there's no reason most of you would have looked at this. It's just so to give you hints so you don't waste a lot of time figuring out how to use the Snap libraries in that context. Anything else? Cool. Now I'm just going to breeze through a few useful graph functions. As I talked about earlier, there's like a graph has this notion of like a generator. So g.nodes allows you to loop through every node in the graph. G.edges allows you to loop through every edge in the graph. One thing that I would call out is you want to be very careful about type in this situation. And what that means is, right, like every node has an ID, like that unique identifier that you called when you add the node to the graph. But then there's this node iterator object, and that's what this is. And so from the node iterator object, or like the reference to the actual node in the graph, you can get the node ID, but it can also do other things. It's an object, not a number. So just keep that in mind. Sometimes your programs will crash because you forget the difference or just don't notice it. Yeah. And then the other things that are useful on graphs, if you want to know the number of nodes in the graph, g.getNodes. And then the number of edges is g.getEdges. And again, just so you don't get confused, getEdges returns the number of edges. Edges loops over it. Not the best naming scheme. I did not create it. And then moving forward, this is useful to parts of homework 0. So the one that's due next Thursday, due on Thursday, October 4th. I don't know if that's next Thursday or this Thursday. And then, so you want to get if you want to count the number of self edges. So a self edge, right? If there's an edge from node A to for all the edges that start and end in the same node, is just count self edges. And then if you want to have the number of unique direct edges, so from A to B, where A is not equal to B, you can use the count unique directed edges. And then the unique undirected edges, I've got a few questions about that. So a unique undirected edge is all of the pairs where, this is also only applicable. Self edges could, I guess, be applicable in an undirected graph, but obviously unique directed edges is only relevant in a directed graph. And then unique undirected edges, again, is also really mostly important in a directed graph. And what that means is the number of unique undirected graphs, or number of unique undirected edges, is all of the number of pairs where either AB is in the graph or BA is in the graph. The other useful functions, if you want to know the in or out degree of a node, you can use dot. So this is again one of the things that you can do with a graph node iterator object. And so you can get the in degree, which is the number of edges going in, the out degree, which is the number of edges going out. And then there's also just a get degree function. So it's dot get degree. And this is all in the documentation, but it's a little different on directed and undirected graphs. And so what that means is that in a directed graph, in degree and out degree are different things, right? Because I can have, in a directed graph, I can have two nodes coming in, or two edges coming in and four edges going out. So my in degree would be 2, and my out degree would be 4. But in an undirected graph, that doesn't really make sense. So in an undirected graph, in degree, out degree, and get degree all return the same number, and that is the degree of the node. In a directed graph, get degree returns the sum of in and out. Cool. And then just very quickly, you can get all the weakly connected components. And so this is what I was talking about with sometimes you need to create these weird snap data structures, snap specific data structures to use on their graph functions. So to get the weakly connected component, you need to create a TCNCOMV, which using our naming conventions means that it's a vector of all of the of data type connected component. And then what you can do is you can call this .get WCCs function and pass that in, components in and the graph in, and it computes it. And then that get WCCs function actually populates the vector with all of the connected components in the graph. And then you can also get the largest weakly connected component. And these themselves, like this, for example, is its own graph that you can manipulate by going over the edges and all the nodes in it. And then the last thing is you can get the PageRank scores. And again, what you see, and then there's also hubs and authorities. We're going to talk about PageRank next week. We're not going to talk about hubs and authorities in this class, but I believe it's on homework 0. You just need to get the score. But you can get the PageRank score of a node, and there it's the same thing. Like you see that there's a hash map from ints to floats that gets passed in to the get PageRank function, and right, that makes sense because the PageRank score is a float, and so what you need is you need a map to store from every node ID, which is an int, to their PageRank score, which is a float, and then it populates it, and then you can also sort it. So yeah, that's all I had. We've got 15 more minutes, and I don't have to go anywhere right now. So if there's any questions that people think other people might find helpful, you can ask them while we're still recording. Otherwise, we can end this, and I can just take your questions.
When are office hours going to start?
Office hours start next week. The schedule should be, so we tried to streamline the schedule location so that everything is in one place. And so now there's a Google Calendar, and it looks like the office hours are not up there yet, but basically there's one set of, I'll send out, I guess I'll put it on Piazza now, is office hours, there'll be one set every day hosted by one of the TAs, and then obviously we'll be on Piazza. Yeah.
To generalize, so if we're doing anything about like attributes of nodes, we'll probably use a hash table into flow or into string, something like that.
Yeah, usually. Yeah, it's a good generalization. Yeah.
Office hours be like one-on-one, or will it be like group?
Yeah, so we'll send out the protocol for office hours. But there's a thing called queue status that we'll use. We'll send you where the location is, and you put your name. It's a computer. It's used by a lot of CS classes. It's a computer program or website. You sign into the queue, and you can see who's in front of you, and then the TA will call your name when it's your turn to get help. Most of the office hours will be in the Huang basement. For those of you watching on SCPD, we will give you instructions for you to video call in to our office hours. So, yeah.
Is this going to be online?
Yeah, I'm gonna post these slides. And then remember, in addition to the slides, the snap documentation is a really good reference as well for whatever you need. Anything else? All right, cool. Thank you, guys.